SwayamPrabha. Digital India. Educated India.
Let us start this lecture with a thought process from great Saint Swami Vivekananda, who says, "The calmer we are and the less disturb our nerves, the more shall we love and the better will our work be." It is a very great statement which is very much essential for us to experience the love so that we can work in a more effective and efficient manner. Let us now recall what we learned in the last lecture. In the last lecture, we looked at the flight of a rocket vehicle, considering its motion in a two-dimensional plane for the simplicity's sake only, and derive an expression for change in velocity, and which is having three components. One is due to the thrust, other is having negative effect, that is due to gravitational pull, and other also is having parasite effect, that is due to the drag effect. And we have also derived a rocket equation neglecting the drag and the gravitational effect, and we learned that change in velocity of the vehicle will be dependent on the equivalent velocity and also the mass ratio. We have defined other various parameters like propellant fraction, payload fraction, and also the structural fraction. And today we will be looking at, using this equation, how we can have a flight trajectory of a single stage rocket vehicle. If you consider launching of a single stage rocket vehicle in a vertical direction, right, let us say this is your rocket vehicle, and it is being launched with a certain velocity v in a, let us say this is your x and this is y vertically, then naturally what will happen, thrust will be acting and it will be going, and the gravity will be putting down, and of course there will be drag and also the gravitational force in the opposite direction of the flight, or the thrust being acted upon it. So it will be moving. However, if it will be launched at certain angle with the vertical axis, let us say this is with which it is being launched, this vehicle having certain angle theta, then what will happen? That means this angle theta will be remaining same, or it will be changing during its flight. This question must be coming to your mind, and let us see what is happening. And we know that the gravity will be acting on the CG of that g, and the drag force on the surface which will be acting, and then we will see that. Let us look at this vehicle considering a very small one, and let us see that. So, we will take this x and y axis, this is the velocity v x which is moving, and this is the v y. Let us say that the thrust is acting along with this direction, making an angle theta 1, and this is your delta v due to the thrust. And on this vehicle the gravitational force will be acting, let us say this is delta v g 1, and there will be also drag force. The resultant change in velocity will be the vector sum of all these change in velocity due to the thrust, due to the gravitational force, due to the drag. Then the resultant velocity will be basically this red one. And if you look at the direction now has been changed, this is theta 2. And keep in mind that this change in direction of the vehicle due to these forces which is acting on that is known as gravitational turn. This is known as gravitational turn, or some people call it gravity turn. And keep in mind that how we will be doing that. I want to find out a trajectory, what I will have to do, because we know that delta V is total delta V due to the thrust, we know that is V equivalent ln mr, and minus what you will get is basically z cos theta dt and 0 to you can say do the Tb, and minus drag by you will have to integrate with respect to time, let us say 0 to Tb. And this already we have seen, this is basically this term is delta Vf f, and we call this term as basically delta Vg, and this term is your delta V drag. Now, it is really difficult to integrate this change in velocity due to gravitational pull, and because of fact that g is changing along with the height. That means it will be also changing with respect to time when the vehicle is moving across the atmospheric, or it is moving along with the altitude. And similarly, the drag is changing, and we know that drag is basically CD half rho AV square into AF, and CD is also a function of flight velocity, rho is a function of altitude, and therefore, it is very difficult to integrate that. So, what we will be doing, we can do it in a very simpler manner by iterative methods, and by taking the small delta t for small delta t is the time steps during which the what you call d by m, the drag for mass also will be changing with respect to time, that and the g cos theta g and also theta, because theta is changing as I told. So, will remain constant. And we can say that this is basically number of steps, iteration step, number of step will be Tb divided by delta t, and we will choose the time step. This is basically delta t is time step, such that it will be such that the all these parameters d by m, g and theta will be remaining almost constant. Then you can calculate this using this vector sum, and then find out how much angle is changing with what is the velocity along with the x direction, and this we can say is basically V x, and this is your V y. And if it is, as I told, that if it is changing in this direction and this is your drag, then the resultant drag will be like this. This is your resultant velocity delta V. You can say it is delta V, because this is your delta V g, and this portion is basically delta V drag. Now, if you consider that the angle has been changed. If I just draw that, this angle becomes theta 2. So, now if it is so, that means then again it will be having drag. So, it will be changing certain angle, right, and this is there, and then again it will be some vector sum of this is your delta V g and delta V d, then this will be like that, it will be moving that way. So, again it will be having this thing and then that. So, that resultant velocity will be this one delta V. This is your V final. Now, after of course knowing this thing, because this step will be small, this will be maybe theta 3 and it will be theta 3 and then this will be your theta 4, and this is goes on, and you can go on doing that such that you will get the velocity V x and V y from this, and by multiplying this delta t in each step you will get basically the trajectory. The trajectory you can because you can this delta t in each space, each delta v, you will have to resolve into this angle component along the V x and V y, and then you can multiply the delta t, or even before that you can do that, you will get the space, and then you can decompose into that, you will get x and y, you will get a trajectory. You can see that the angle which is there here theta, and it has been changed. If you look at this angle, this has been changed very much, with respect to this one, that angle has been changed. So, this is known as gravitational turn, and you can find out the flight trajectory by that, by doing a numerical calculation by iterative method. That means, you will have to use basically iterative method to calculate the flight trajectory. And if you take this time step too small, then of course you will have to compute for a longer period of time, but you will get a very accurate flight trajectory. Now we will have to look at basically, as I told, this is flight trajectory calculation procedure for a vehicle with a gravity turn that we have discussed, and let us look at burned out distance. A question might be coming to your mind, what do you mean by burned out distance? It is basically distance traveled by a vehicle from the launching time till all the propellant being burnt out, being exhausted out. That is the distance what it has to be looked at it. So, the distance covered by the rocket vehicle from initial launching time to the burned out, and which can be determined by neglecting the drag effect. Of course, one can consider drag effect to get the accurate value. For the time being, we are looking at that, not considering the drag effect or by neglecting the drag effect. So, we need to basically find out the distance S b, considering both the contribution due to the thrust and due to the gravitational pull. So, that is the thing what we will be doing. So, that is basically, if you look at, this is nothing but your velocity v into dt 0 to T v, and T v is your burn out time. This is known as burn out time. So, how we will get this relationship burn out time v? If we know that delta v, let us say this is your equation 1, but earlier we have derived expression for delta v, that is delta v is equal to, we know that is v equivalent ln mr, right, into this is basically g cos theta, and if I take this average, that means it is not changing with respect to time, and this is with t. So, that we can say right, and this is for a certain period of time. Now, this I can write down, this is already we have derived. So, I can write down V, we know that delta V is equal to V minus V naught, and so that we know that delta V is basically V minus V naught, and V naught is the initial velocity, and in some case initial velocity will be 0 if it is launch from on the surface of the earth. So, therefore, or if it is being launch from the itself like with having certain velocity. So, V naught has to be written. So, therefore, we can write down V is equal to V naught plus V equivalent ln m r and g cos theta minus t. So, I can write down this is basically equation 2. So, I can we can now combine this equation 1 and equation 2, we can get by using equation 1 and 2, we can have S b is equal to 0 to T b, that is V naught dt plus 0 to T v V equivalent ln m r dt minus 0 to T g cos theta, we are saying this remaining constant T dt, this is T b. So, of course, it is very easy to integrate the first term, because if V naught will be remaining constant during its flight. So, therefore, it is not changing very much, and that is V equivalent is also a constant, but ln m r is changing because of fact that if you look at the mass ratio we know this is your mass ratio, right, and mass ratio is changing. Let us consider total mass will be initial mass m naught minus m p, m p is the mass of the propellant, T b into T, this is your mass of propellant or propellant mass. So, I can write down this as basically m naught minus m p, right, and divided by the m naught T by T b, and I can also divide it by m naught here, I can divide it by this m naught here. So, this will be equal to 1, and this is equal to, look at, this is your propellant fraction, what we have already discussed. So, this is nothing but your 1 by m r. So, I can write down that 1 by m r is equal to 1 minus P f by T b and T. That means, the mass ratio is changing with respect to time, right. So, that you should keep in mind, and of course, we will have to now integrate this term. This is a term which is difficult to integrate, we will see how we can integrate. And if I consider this is the term gravitational term, that is, if I take g cos theta is not remaining constant with respect to time, then it will be very easy to integrate. So, let us consider how we can integrate this, that is 0 to T b V equivalent ln m r dt is equal to, I can write down 0 to T b V equivalent ln 1 minus P f by T b into T dt. Let us say this is your equation. Let us consider, let 1 minus P f by T b into T is equal to x. So, therefore, I can write down P f, and there should be a minus over here, P f by T v dt is equal to dx. So, therefore, we can write down that here also the boundary condition, and keep in mind that this boundary condition for that, if t is equal to 0, if it is t is equal to 0, then what will be the x is equal to 1. If t is equal to T b, then this will cancel it out, x will be equal to 1 minus P f. So, we can write down here that is minus 0 to T b. I can take this V equivalent out, V equivalent. Keep in mind that this minus we have taken because this is basically when we say V equivalent ln 1 by m r, therefore, we take is minus, and that is ln. I can put this as a x here, sorry, this I will be expressing, this is basically nothing but your x, and in place of dt I can put that. So, that this will be ln x and minus T b by P f, that will be dt, and if I change this, integrate this thing, that is the range, that is from x when t is equal to 0, this will be 1, and this is 1 minus P f. So, if you look at, I can write down that here, that is minus became plus. So, this became V equivalent T v by P f. I can take this out, and this is 1 minus P f ln x dx. So, this we can integrate ln x dx from 1 to 1 minus P f by using variable of separations, and then we can get that is basically I am writing directly, that is V equivalent T b by P f. I can write down that basically x ln x minus x 1 minus P f. So, if you simplify these things, and you will get this is equal to V equivalent P f T v, you will get 1 minus divided by P f ln 1 minus P f plus 1. So, by integrating you will get this term. Now, we know that we can express this propellant fraction, that is P f is your propellant fraction, in terms of mass ratio. We can do that very easily. We know that m r is basically equal to 1 minus 1 over P f, and if we want to find out basically P f will be equal to 1 minus 1 by m r is equal to m r minus 1 by m r. When you will substitute this P f and also 1 minus Pf in terms of here in this expression, you will get this integral is 0 to Tb V equivalent ln mr is equal to V equivalent Tv 1 by mr minus 1 ln 1 minus mr plus 1. Let us say this is equation basically 4. By using equation 3 and also integrating the terms using equation 3 and 4, while integrating these terms, like we will get that velocity is expression for SB is equal to, this is V naught Tb plus V equivalent Tv mr minus 1 ln mr plus 1 minus g cos theta Tb square divided by 2. So, you can see that from here, this is your expression for the burnt out distance without considering the drag effect, and you can see that SB is basically function of the V equivalent means ISP also, right, specific impulse. It is a function of mass ratio. It is function of also the g and angle g cos theta, but if you take it constant then it will be not, and also V naught, but it is independent of the drag, right. It is not, because it is not depending on the size of the vehicle, as we are not considering the drag. So, you can see that MR will be higher than that, this SB will be lower, and this is having a parasite effect. It goes by Tb square. That means, if the duration is more, then the length distance will be travel will be less, because it is going by Tb square. Therefore, we always take a particular in gravitational field smaller time, so that this parasite effect can be minimized. You should keep in mind. And now we will be looking at the coasting height. If you look at coasting height, it is the basically height gained by the rocket vehicle beyond the burnout. Generally, it is the vertical height what we consider. If I consider a rocket vehicle here, if it is going to move over here distance, let us say it is moving at certain distance, is known as HB vertically, and then at this point, this is your burnt out time. It will be having some kinetic energy, that is Vv, due to the Vb, that burnt out velocity, and then it will be moving till it all this kinetic energy getting consumed. So, that this height, whatever height it will be travel by that, this is known as Hc. So, this Hc will be basically will be the rocket vehicle will be traveling till this kinetic energy is consumed. That means, we can find out this coasting height Sc by balancing the kinetic energy of the vehicle to the potential energy gained by the vehicle. This is a very simple thing. That means, this is the burnt out mass of the vehicle into Vb square divided by 2, this is the kinetic energy at the burnt out time, is equal to, basically we can integrate as mb g and dh, and this is from basically 0 to SC, because here we are considering the height 0. So, if I consider the gravity is having gravity is not changing at that high altitude, then you can take it out and you will get mb g SC, and this is cancel it out here. So, you can get SC is basically VV square by 2g, and this is your coasting height. And total height, or the maximum height gained by the rocket engine is, that is HB, that is HB from here, and HB plus SC, and HB or the SB you can get that thing from the equation 5, and in this case this cos theta won't be there because cos theta is 0. So, therefore, it will be only GTV square by 2, this term will be coming HB plus VV square by 2g. Keep in mind that this coasting height is very much essential, particularly for sounding rockets which is being launched for finding out weather conditions and other things. And this coasting height is much higher than the burnt out distance, because of fact that the coasting height is goes by the VB square. So, if higher the burn out velocity, then higher the coasting height will be. So, you should keep in mind that, and of course, if it is not a vertically, then we do not call it coasting height, but there will be projectile, right, distance one can cover, that is easy to calculate, you can do that. And with this I will stop over here, and thank you very much for watching this video. Thank you very much.